direction they're moving. You can think about, for example, the Earth has some rotation, and I don't even know if it's left-handed or right-handed. On a macroscopic scale, the universe doesn't actually have that kind of preference for left-handed or right-handed. So it helps to think about that spinning as in this classical sense, that something's actually spinning. But it's an inherent property when we're talking about particles.
May I
Yes.
here? You mentioned chemistry. Indeed, there are molecules which are mirror reflection of one another. There is no surprise if these molecules are flat, if you understand what I mean. But if they are three-dimensional and you do the reflection, then in the mirror, then there is no way how you can turn one to another by rotation. The reflection changes them. And what is interesting, their chemical property also change. One might be molecule, my friend chemist gave me example, I don't remember how it is called, but same molecule can be a poison and can be a medicine. The difference between them, they are reflected. And it is even more striking that this asymmetry exists in biology, because our DNA spiral is left-handed. Why is that? Why is all the mirror stuff, why all the living stuff is built of the left-handed DNA? It is a puzzle. It does not mean that you cannot make a right-handed. And this right-handed DNA also exists, but they are very rare and they don't participate in the living species.
Have any organic molecules extracted from meteorites shown any different properties?
I did not heard that, but possibly, maybe it's possible to find some. Chemists can do that. They can do right-handed and left-handed, and they are also wondering why is chemical properties is different. Chemical properties mostly in a sense of interactions with the biological systems. And this might be because biology is left-handed. So that the different right-handed and left-handed chemistry will work differently.
You have a question to that? In the back.
Yeah, so, I mean, like, ultimately we're talking about entropy at some point, right? I mean, like, decay going on, the arrow of time was mentioned, and it almost sounds like in the reflected universe, like, you might be getting into the probability of reversing entropy?
No.
Okay.
That process is the same. The only difference between the two sectors is that the weak interaction would prefer to couple to right-handed particles. In our universe, it prefers to couple to left-handed particles. So it's actually, it wouldn't look so different to us.
This would be the same.
I'm no chemist particularly, but I understand that if you make a molecule, let's say an amino acid, synthetically, that you get roughly a 50-50 mixture of left and right-handed molecules. But if that happens to be, if you're taking a supplement and you've got taking a mixture of left and right-handed, your body only uses the left-handed molecules. Is that correct?
Or right-handed will be a poison.
Sometimes, but not always, right? It's not always a poison.
Well, I'm telling as an example.
Yeah.
I don't know that in the mirror universe even that would change, however. I think that if you have a preference for left-handed molecules, that's not a cause of the weak force. So that actually, even in the mirror universe, you might still see left-handed DNA and left-handed preference for chemicals. I'm actually not sure why that's the case. It must be a different reason, although it's intriguing. Okay, sure, in the front.
Would you be able to entangle molecules, one in each?
That's a very interesting question.
entangled.
Yeah.
So, that's not good.
What's the word, when the anticipation builds, that's a very leading question. Maybe that's a good, I might take one more, and then maybe that's a good way to segue into the next few. Well, okay, sure, yes.
Okay, with the predominance of left-handed particles in this universe that we can tell, does that predominance possibly show a relationship to, say, regular matter versus dark matter, or?
So the question you're asking is, maybe say it one more time. I just want to make sure if I'm understanding what you're getting after.
So what we're seeing in our everyday universe is largely left-handed.
So we're seeing left-handed and right-handed particles. However, the weak interaction. So the weak interaction prefers so particles are more likely to decay if they have a left-handed chirality.
Okay, well, in that case, are we seeing equal quantities of right and left?
Well, for example,
chirality?
electron, you are all familiar with electrons that
Yes.
is in every atom. It can be left-handed and right-handed electron, but the weak interaction will interact only with left-handed.
So not much changes. It's just whether the weak
It
interaction
is the
participates.
structure of interaction of the world, and in another world it might be another structure that it will like to interact with the right-handed because it is symmetric, but symmetry is broken. And people thought that this is not good if symmetry is broken. And at the beginning, when the discovery, which you saw in the movie, was made in '57, before that, many people thought that this is just impossible. It cannot happen that the universe will be asymmetric. Then they have to digest that it happened. So that since then we see that many symmetries are being broken, and C symmetry is also broken, and T symmetry is broken.
And these symmetries are really very interesting. They're tied to very important questions like why we're all made of matter instead of antimatter, and so we like to study these symmetries because there must be, we feel and we believe, but perhaps that is not fair. The laws of physics are whatever they are, but it seems like there must be some greater symmetry to tie the whole universe together.
Well, if these, if the particles with right-handed chirality don't interact with each other via the weak force, how are they existing? I mean, how do they show up in our universe? Just as sort of
Nothing
random
prevents that.
particles?
It's just whether or not, so the weak force is responsible, it's weak. It's not as weak as gravity, but compared to electromagnetism and the strong force, it's very weak. So it has a small perturbation in our everyday life. But it is what's responsible for particles decaying into some particles, or nuclei decaying into nuclei we might not have otherwise. So if it, I suppose you could say, if it coupled to both left-handed and right-handed, perhaps that would happen twice as fast. Although you're sort of saved a little bit, maybe this gets, I'm going to say relativistic shifts, but maybe that's too technical. Because you can, if you just move faster than a particle, suddenly it looks like it's moving in the opposite direction. Now that suddenly looks like it's right-handed. So it's actually, it turns out to be kind of a soft effect, except for really light particles like neutrinos, which we barely can detect. So it's not a large effect, I would say. It's an interesting.
May
that's too
I add
technical.
something? That,
Sure.
This movie is certainly interesting, but it would be also true, and everything there would be true 60 years ago. It is not something which is new. What we are trying to do
Yeah,
is a
we-
new thing, and
Forward.
I would rather ask like you asked about the dark matter or entanglement of these two things, that is the new things which we are trying to explore.
So I have you raising your hand twice,
Oh,
but
oh.
maybe we can
Well, I have
do that.
Every time somebody asks a question, I think of something else I want to ask. So,
Sure.
popping back 3 or 4 questions ago, yeah, I was with this is a topic that's connected with dark matter. Dr. Kamyshkov just mentioned it, and there was I saw a presentation that Dr. Kamyshkov did in April. It was live streamed on Facebook, so I got to watch your lecture in April, and there was a slide where you described the properties of what we would expect mirror matter to have, and they overlapped with properties that we expect that dark matter would have. That, like, for example, it would be invisible to us. Can you talk about the similarities between the experimental mirror matter and how it's similar to what we think dark matter is?
Okay.
Easy question.
Easy question.
You really think
slide,
about it?
you just can say that they are the same.
The particles are identical in this model. So
And
the
between-
weak interaction is sorry. The weak interaction might be right-handed.
So that's your
instead of
thesis, is
left-handed.
that the
And
mirror
that's-
matter
it's
is the
really
same as
quite
dark
similar.
matter. Okay.
Now, we know a lot about dark matter. There's a lot of evidence. We have a lot of confidence that this is a very likely explanation for what most of our universe is made up of. And we can infer some properties about how this dark matter, and based on what we can calculate from how the universe must have evolved after the Big Bang, from all of that, this gravitational-based evidence that we have, we understand some things about mirror matter. So we know that the two sets of universes, now these are particles coexisting with us, but it's convenient to call them universes. But we know that they must be different in some ways. Because of the physics limits that we have, it doesn't look like dark matter behaves exactly the same way as our own dark matter, or our own matter, our own visible matter. So there's some macroscopic differences. The universe might have been born with a colder temperature, so it would have evolved a little bit differently. Not very different temperature, but just a little bit, about a factor of 5 difference, why not? And that could help it explain, that would change its properties enough to explain some of the observations that we see. So there's some macroscopic changes. The stars would look a little bit different, maybe there's more dust. The most common elements in that kind of universe would look different. So it would look very different and hostile to us, but the laws of physics would look identical.
So, for example,
Except for the weak force, sorry.
well, so for example, one of the properties that I recall from either the lecture or from other reading is that if you had collections of mass of normal matter and dark matter, that they would essentially pass through one another because they don't interact. Is that because of the weak force not operating on the...
It's because the two sectors can't interact. They just don't see each other. There are different, very high-level theoretical
Except
models
by
for
gravity.
why.
Except
They
Except by
don't.
gravity.
They can't interact. The forces don't interact. Gravity is actually not on this chart. Actually, it is. No, it's not. Okay, good.
No.
Gravity's not on this chart. That's sort of been the most difficult for us to understand how to include in our standard model. It's the most familiar to the average person, and it's the one that physicists are having the most trouble with. But that gravity behaves differently. It doesn't behave like a force in the same way. It seems more like maybe a distortion of space-time. So it's clear that dark matter and visible matter both feel gravity, as far as we can tell, feel gravity in the same way. And there are different advanced models of gravity, different gravitational models that people have proposed, and I'm not going to talk about those.
We think dark matter and gravity interact because of the effects, the visible effects, like gravitational lensing.
Because of our gravitational observations, it behaves like it feels gravity. That's right.
So it's having an effect on,
Yes, so if we could build an experiment as big as the galaxy, we probably would be able to understand exactly what dark matter is. And until then, we'll try our best with, particle physics methods to find there might be, we hope, there might be some other very weak interaction that we can be sensitive to on our non-galaxy lab scales. And that's what we're able to do in particle physics. We're able to look for some small, feeble interactions between these two sectors, and this is everyone's attempt to try to understand dark matter is based on, we hope there's a small interaction between the two.
And this is
we
related
can-
to your question about entanglement. We assume that some particles in this sector and this sector can be entangled. They can, that means that they can know it about each other, and they can transform from one to another.
I might just skip to that.
And neutron is an example of that. And this is exactly what we are doing. We are looking for this entanglement with the neutron, and we are looking how to break this entanglement.
So this is what we actually call the oscillation. So here's just a cartoon. I'm a scientist, not an artist, but this is what I would describe it as an oscillation. The neutron can, let's see, the neutron can sort of, you can think of it as a rotation. I don't know if that's going to be a good analogy, but you'll be my guinea pigs. You can think of it as a rotation. That if I'm looking in this direction, I'm a neutron, and if I'm looking in this direction, I'm a mirror neutron. And maybe the neutron can kind of slowly rotate and start to see a little bit in this direction. And so it sort of has some small probability to be looking in the mirror neutron direction. But mathematically, that's kind of how we think about it. And so if we can cause an oscillation to occur, if I can create some probability to be looking in the mirror neutron direction with enough neutrons and with some way to sort of filter these, maybe I can maybe I'll take your question because I think I might be failing the experiment to explain this.
Do those two different directions have different energies? Like
That's a
an
good
electron can bounce up, but they're discrete bounces. It's not continuous.
So that's a really interesting question. In fact, that kind of hits it on the head a little bit. That is actually one way in which we can control how quickly or how probable it is a neutron could change directions. If the neutron and the mirror neutron had exactly the same energy, the probability would actually be highest for us to be able to create a chance for the mirror neutron to entangle or to oscillate into a mirror neutron and increase our probability to find it in that mirror neutron state.
And when you say oscillation, are you talking about just going back and forth between
That's
the
a great way to think
two
of it. That's
states?
right. I'm just literally oscillating back and forth. And if I waited a really long time, I would actually see a neutron just slowly oscillate back and forth between its neutron state and its mirror neutron state. It behaves just like neutrino oscillation.
So it's like a maximum
You know
and a
about those.
minimum in a sine wave.
That's exactly right. So a sine wave is a function that just like a wave on the ocean, it just goes up and down. And
Well,
that's how this would behave.
Let me add to that we believe that it is oscillation happen, and the magnitude of this oscillation is not very large.
Sure.
But it does not mean that they are like everything in quantum mechanics. I don't know whether you discussed quantum mechanics here. It does not mean that they physically became neutron, became mirror neutron. In order to do that, you have to have some interaction which will distinguish them. Unless you make this interaction, you can predict what it will be there, but you will not have a real mirror neutron or ordinary neutron until you will pick it with something.
So the familiar example that I think many people in the room might have heard of is the Schrodinger's cat. it was kind of a thought experiment that I'm abusing a little bit, but you have a cat that lives in a box, and some probability for poison to put the cat to sleep. I don't like the animal cruelty. And you don't actually know at any given time, is the cat still awake or is it asleep? And you can't know until you perform some measurement. Now, of course, if you open the box, you can imagine opening the box being like a measurement. For some reason, that forces the cat to have to choose. And I don't actually understand that. And I think this is kind of an interesting philosophical question in physics, is what does it mean to be a measurement? And why does that force the cat to choose to be in, awake or asleep? That's an interesting, I think still today, philosophical
I
question.
never did like that.
Yeah.
With the animals,
Cat
right?
thing, I think it's a cop-out.
Well, yeah. So
Exactly.
I'm using it for the familiarity, but I recognize it was originally brought up to show the ridiculousness of this
I
scenario.
understand.
But it's a similar concept. The neutron has some probability to be in either state. Another way to think of it is it might be not quite looking totally in the neutron direction and not quite totally be looking in the mirror neutron direction, but it has to decide once it approaches a wall. A neutron is visible matter, and it's going to hit the wall, and it's going to stop. A mirror neutron is dark matter. It's not going to hit the wall, and it's going to go forward. So if it is in this kind of offset state, it has to make a choice. You can't have part of yourself fleeing past you because the mirror neutron part of yourself is continuing through the wall. You have to decide, okay, I'm going to be the mirror neutron, and I'm going to go through the wall and take the leap of faith, or I'm going to be a neutron and stop. So
Back
that's
to the
interesting.
electron in the discrete states. We say that the electron jumps from one state to the other, but is there a time when there's an input of energy before it jumps, that it will receive a little energy and then it jumps?
Yeah, of course, that is all
And
described
if the
in
same
it is
could
all
be-
described by quantum field theory, that how that this transformation of electron happen. Electrons have nothing to do with the transformation we are talking here, because it should be neutral.
I'm just using it as an
Right.
example of jumping states, and maybe what happens here, because you keep saying it looks a little
No,
bit.
it's, the physics is a little different. It is not waiting for the jump. It is waiting for zero energy. When you create external condition, that energy is not, is the same, then there will be most
Right.
probable chance to see that one will be converting to another. But you have to measure that. If you don't measure, they will oscillate back.
Okay. So it's almost the opposite. It has to achieve a zero state and not an excited
Right.
state
As close as
before it
possible.
jumps. Okay.
What kind of frequency range are you talking about, these oscillations,
Quite
Seconds or
long.
gigahertz or what?
No, quite long. So,
Oh,
the times that we're sensitive to are, so far, the sort of characteristic oscillation time, depending on the mechanism, we might be sensitive to 10 seconds, we're hoping to get up to 100 seconds, and, probing up to 15 minutes is pretty interesting, because that's the lifetime of the neutron, and probably we can't do much better than that.
But when you put it in magnetic field, it change the energy and start oscillate more with high frequency, but with smaller amplitude.
Okay.
Right, so maybe there's too many ways to answer the question, because it kind of depends what mechanism you're looking at, and I guess there's
Lee is
both
talking
field
about,
and
about
also
vacuum
lifetime.
oscillation.
Right, yes. I think you were first.
Okay, so with the oscillation, when you go to measure the position, you're going to find it at either neutron or mirror neutron, but not in between.
Right, so you can't be in between, and that's why the experiment works.
But the the fact of an oscillation implies in-between states exist.
That's right.
But
So-
you can't see an in-between state.
So how about I walk through this little diagram to explain kind of what's happening. We know we start with neutrons because we have a reactor or we have an accelerator that exists in the visible universe. So we know we're starting with neutrons. And we can use magnetic fields to create this oscillation, this chance to kind of start to either quickly or slowly, depending on what the state of the fields, we can change how quickly the neutron has a chance to become a mirror neutron. But it's existing in both states. It's a little bit, it's not quite looking in one direction or the other. It is existing in both states. And it's only when we create some measurement, something to force it, for example, this wall, that forces it to be in either one state or the other, because the neutron has to be stopped and captured by the wall. The mirror neutron is a dark matter candidate, so it can go through. So that's one component of this experiment. And then once we are on the other side, we know that neutrons can't get through the wall. Some of them can, but we can calculate how many, and that's a background for us. But most of the time, neutrons can't get through the wall. Only mirror neutrons can. And those, again, can go through the reverse process. They can start to build up some probability, now looking in this direction, to be looking in the regular neutron direction. So here, you are actually in both states. And it's not until you get to the very end where we say, I want to detect a particle. I can't detect a dark matter candidate, but I can detect a real neutron. So again, this acts just like the wall, except this wall tells us if it saw something or not. So that's how we do it. We know that it's only if the mirror neutrons, if you have a probability to be found in the mirror neutron state before the wall, and have a probability to be found in the regular neutron state after the wall, that's the only way we can see a signal.
So, not really knowing the scale of what you're measuring, but theoretically, if you measured soon after your neutrons were either stopped or passed through the wall, you would see more mirror neutrons than if you went another distance out,
The distance.
where you might start to see them equalize again.
So that's a great point, and it kind of depends on the configuration. Ideally, in some configurations, you actually want this to be as long as possible. You want to give, in some configurations, you want to give the magnetic field time to allow the neutron to oscillate towards the mirror neutron state. Or, no, I don't know, I don't want to get too technical, I guess.
Go for it.
Well, in our example, we had actually an interesting magnetic field profile. So as the neutron was traveling through the magnetic fields change the energy state of a neutron. So that actually changes its probability to be found in a mirror neutron state. So where we position the wall, and in some configurations where we position the detector, should change how many mirror neutrons we're ultimately producing. Absolutely. And that's very important because this is such a rare process. Something rare has to happen twice. We have to have a small chance to be found in the mirror neutron state, and then of those, a really even smaller, or a small chance with even fewer neutrons to be found back in the regular neutron state. Meanwhile, we're in a facility known for making lots and lots of neutrons, and those are an important background for us. So being able to change positions and change the path that the neutron sees is extremely important for us to know that we're doing this experiment correctly.
Are you doing this at the SNS?
We did our first experiment at the Oscillation neutron source this summer, and ultimately we'd like to use the high-flux isotope reactor. The instrument we want to use is undergoing some upgrades right now, which are kind of interesting for us to make our experiment a little bit easier for us. But we've already done one.
I would like to stress what Leah said, that so that leave no misunderstanding here. We cannot see mirror neutrons.
Yes.
We only can see how they are converted back into regular neutrons. And for that, we have a wall very thick. And if it is not thick enough, we will make it thicker. So the neutrons will not come through the wall, but mirror neutrons will not even feel that. They will go through, and in the next space they will be converted back, regenerated, and we will see them as neutrons. If we would do such experiment not thinking about mirror matter or dark matter, say 20, 30 years ago, we would say, well, we see something unusual. We have a wall, and the neutron somehow goes through the wall. How it can happen? But now we have a clear picture how it can happen, through mirror particles.
So I'll have you next, go ahead.
Why are you looking specifically at neutrons to oscillate to mirror matter? Why can't like protons or?
That's a great question. So we try to disturb the laws of physics as little as possible, and this is already a big disturbance. If protons could oscillate, that would mean we're violating charge. Charge would be disappearing from our universe, and that's one we don't want to. That's a symmetry we don't want to violate. So when we're talking about oscillations, we are only ever talking about neutral particles oscillating. So anything in the universe is possible as long as it's not forbidden. We know violation of charges is forbidden. We believe so. To a very, very good limit. That has seemed to be true. But neutral particles can oscillate. And the reason we're interested in neutrons is we've got them. And no one's really tried to look very hard for a lot of these techniques before. So, in some sense, I didn't really need a mirror universe to be motivated to do this experiment. Let's just try this experiment and see if we can make neutrons disappear into some other dark matter candidate, any neutral particle. We know neutral particle oscillations can happen. We see it in a lot of other particles. For example, most famously is the neutrino, and this was it 2015, the Nobel Prize? The discovery of neutrino oscillations. So this is standard physics by this point. So why not the neutron? Maybe the neutron can oscillate.
Actually, there is another group at Oak Ridge National Lab which is looking at the sterile neutrino, oscillation into sterile neutrino. It is similar idea what with neutrinos. So then they are actually doing it much more time than we do, but so far without success.
Yes.
So the first question is really a joke. And the second more important question is going to be, what are you doing this for? But
Okay.
are you all blasting a laser into a wall, into another dimension to bring something, like Stranger Things?
So, I kind of cringed a little at that description at first, but maybe it's not a terrible description. I mean, in some sense, the neutrons, it might be easier for the average person who's not familiar with concepts like oscillations and so forth to understand, the neutrons are going into a portal to become another type of particle that we can't interact with. That's not totally unfair, and that portal lets it go through the door or go through the wall, just like any door would. So it's not actually that bad of a description, although that's oh man. That's very go ahead.
You can equivalently say that there is a new force which makes that, and that is another language for the same process, either through the door or through the new force.
That's very dramatic. Sells newspapers, I guess. And then you said, well, you had a second part to the question.
So what is the I mean, it may be too early, but like the long-term application of this?
Man, I mean, one of the biggest questions I think that we face in science is what is the majority of our universe made of? So that's the application. I mean, you discover a new force, you discover a new particle. You can only imagine what to do with that. What do we use? What has gravity been good for us for? What major applications have we been able to take advantage of from electromagnetism? One can only speculate and write sci-fi stories about this sort of thing.
You see that scientists are very conservative. They're afraid to talk about their far-fetching fantasies. But if you can think on a science fiction side, then you can say that the most of the matter in our universe is dark matter. If it is mirror matter, we will understand how it works, and if there is a transformation from one to another, maybe we can find a way how to facilitate this transformation, and maybe this will be a way how to get energy from the dark matter. You know, I cannot tell you how exactly. I can, but I will. But that's what might happen as it is. Because look, more than 100 years ago, nobody thought that there are nuclei in atoms and that there is some energy there, and you can break this energy and make electricity from that. Who knew about that? Maybe there is a similar situation with that. When we will find how it works and we will learn how to manipulate that, maybe we will have access to this energy.
Yes.
Maybe I'm missing something here, but it seems you've got a wall, you're doing something with a real neutron on one side, and then you get something appearing on the other side. So you're measuring those two. You can't measure anything else but those two, right?
That's right.
So,
Then,
go ahead.
how do we know there is not some intermediate state? If you can only measure the two endpoints, the maximum and minimum, how do you know there isn't an in-between?
We should not measure anything on the other side if it is all the same.
But then how do you
If
know it's
dark.
there if you can't?
So, maybe I'll answer your question in this way. We know that the laws of physics as we understand them must be violated if we see a signal, and one possible explanation is what we've described. But of course, we're not measuring what the mirror neutron is doing, and we could, once we see an effect, come up with clever experiments to study the properties of what's happening in the middle. But all we know once we see a signal here is, well, that's weird. And then I think at that point you have to start to say, okay, does the mirror neutron oscillation describe this? Or is it something like an intermediate state? So far, this just tests our laws of physics as we understand it. And then if we see an effect like this, I think the next step is, well, does it behave like a neutron?
We have some picture how it happens, which is based on physics,
Yeah.
on some laws, on some predictions, and some connection with other fields of physics. And because of that, we think how it might happen. If you have a different mechanism in mind, there is some intermediate states, tell us. We will tell us how it will work, and we will test it.
This experiment.
I'm trying to, but I don't have the vocabulary. If you take your signals from the start and your signals to the end, do they account for 100% of the time?
So we actually don't have signals at the start. We have signals at the end, and we can change things in the middle and see if anything changes. So we can change the magnetic fields in ways we understand. We can change where the wall is in ways we understand. And we know that how that should change our signal. And if we see a change that's different from that change, or if we see no change, then we know things are normal. If there's no change, that's what we expect. The neutron shouldn't care where the wall is, and the neutron shouldn't care what the magnetic fields are. It should just not go through the wall. But if there's some strange mechanism, some additional mechanism, the only detector we have is this one. So we're just looking to see if we can make any kind of change in the middle of our experiment to create neutrons in our detector.
But how do you know what you're starting with if it gives no signal?
I can take the wall away.
We turn on magnetic field.
No, I take the wall away, I see a bunch of neutrons. I know how many neutrons are usually hitting my detector. And then if I put the wall back, those neutrons should stop.
But it is still not enough.
No, sure. You change the magnetic fields, you move your sample.
Switch on or
change
off
the speed of
magnetic
the
fields, and we will see effect dependent on magnetic field, which is crazy, which should not be.
Not necessarily.
Well,
No, I mean, the first, it's a good point. I will get to you, sorry, but it's a good point. It's possible that magnetic fields could cause real neutrons to go through the wall, for example, if there's a magnetic field dependence to a capture cross-section, and suddenly the chance that the wall captures neutrons goes down because there's a magnetic field that's applied. That we might be able to see, and we'd see neutrons going through the wall, and it would look like the magnetic field is causing that. But it's causing real neutrons to do it for real physics reasons. And if we see something like that, we just do a second experiment to look for and measure what is the capture cross-section of the magnetic field. So if we see nothing, the experiment's very easy. It's only if we see something that we have to think really hard, okay, something's weird. That's weird. That's the right answer. We don't know if it's an intermediate state or mirror neutrons or something really mundane that we just didn't expect. And all of them are interesting. Some of them are more interesting than others.
So you admit that it's possible that there's an intermediate state. You just said you don't know if there is one, which to me is tantamount to saying there could be.
Sure,
yes,
why not?
yes,
Okay.
it can be intermediate state, but we don't know what to do with that.
Right.
If you know, then fine.
Yeah, we'll get lots of theorists
I'm
interested
working
once
on
we
it.
see. I'll take your question and then I'll take yours.
Okay, if mirror matter is subject to electromagnetic forces as regular matter is, why is it not detectable?
Mirror matter is subject to mirror electromagnetic forces. So there are mirror photons which mediate the mirror electromagnetic force. So it's actually never going to feel our, well, okay, there are some theories which propose some small coupling, oh dear. But in the simplest model, there are no interactions between mirror neutrons and anything but gravity and in our sector. So electromagnetism, that's firmly in our universe. So except for some theories, which are also interesting and we can explore, we expect a small or no interaction.
Okay, how about a double slit?
Double slit.
A double slit experiment, you know.
Yeah, double slit experiment show that there is interference
Right.
of the wave function when it is either go this way or go this way.
Mhm.
In the end, it will come to observation of the electron, photon, whatever you like. This is the similar thing. It is, we don't know whether it will go through the right slit or left slit, but at the end we know that we should see the same thing, either in this state or in this state.
Mhm.
It is both follow the quantum mechanics. Is it answered?
That's an answer.
Yes.
So if I understand it correctly, the number of times you are hitting the neutron at the wall, if it is in the mirror neutron state, then it passes. If not, it stays. It's not like it's neutron, it hit it, like okay, then it transformed to mirror and then it moved, right? So if it was in the neutron state, then you can't detect anything on the other end. But if it was in the mirror neutron state, then you probably can detect something. So by the number of times you are hitting and the number of times you are getting it there, can we talk about the probability that it is in this state, like the amount of time it is in one state or the other?
Yes,
Does it relate to
that's exactly what we're trying to measure. And that's really all we have. If we assume that that's the correct model and it's not an intermediate state, that's how we do this. We take the number of neutrons we detect at the end, and we can convert that into some probability. We know we're getting, for example, 10 to the 8, 1 followed by 8 zeros, neutrons on one end of the wall, and maybe there's a 1 in 10,000 chance that I turn into a mirror neutron by the time I hit this wall. And then maybe there's a 1 in 10,000 chance that I turn back into a regular neutron when I get to the other side of the wall. That would mean I'm seeing 1 neutron per second more than the regular background from everything else happening in the room. So that's how I do the experiment. I say, compared to compared to a measurement where I know there's no possibility of neutrons transforming, how many more neutrons am I seeing? And that number can directly be converted into the probability. And that's exactly how we do the measurement. Yes?
Do the characteristics of the wall predictably affect your experiment?
We worry about that, so we try to make it as thick as possible to avoid that possibility. We try to make it as far away, so our wall is actually a tube. The neutrons go into a tube, and there's a wall at the back of the tube. And so if neutrons can't bounce back and get around the wall and hit our detector, the material that we use is boron. Boron has a very high probability to absorb neutrons. Neutrons can actually go through walls just fine. There's no quantum tunneling or anything like that. It's just a very high probability to be captured by a nucleus. And the wall's thick enough that something like maybe 1 in 10 to the 12, we think, are actually going to get through the wall normally. And that's too low for us to even measure. So far, we haven't measured any neutrons getting through our wall in a background state. But maybe a different material could have, for example, if we're worried about the magnetic field changing the number of neutrons going through, another thing that we thought about and tried is using a different material behind the wall that might have a different dependence, for example. So yes, all of these things matter, and they matter a lot more if you get to that state where you say, well, that's weird.
More often, it's like liquid and solid state materials. Just if you sit at the same number of nucleus, it's like, because that doesn't affect anything, whether it's liquid state or ordered state.
It's all about probability for the neutrons. Solids are much easier for us to work with, and so from a pragmatic point of view, that's what we would work with. But water is very good at stopping neutrons. Mercury, oh yeah, mercury. Yes.
So, I saw your friend ORNL lecture
Oh,
last month, and it occurs to me to ask if you took these neutrons and brought them down to a temperature where you could pour them, say, and turned your experiment vertically, what would you expect to see? Would that have an effect on transition between mirror and visible?
So you're wondering the going horizontally versus going vertically?
If you poured your neutrons like you were pouring from your flask, your very cold neutrons,
yes.
through the tube and had your wall and then your detector at the bottom, would that make a difference?
Yeah, so that would be, it would in a lot of ways. That would be kind of a different and interesting experiment. And actually, everyone so far except for us uses those kinds of neutrons to search for mirror neutrons. Because you can make neutrons have so low energy that you can actually store them in a bottle. And most people who look so far, the people who have tried to look for this effect, pour the neutrons in the bottle and change the magnetic fields as the neutrons are just stored in this bottle, and they try to see if any of them disappear faster at at specific magnetic fields. If there's a magnetic field dependence to how fast the neutrons disappear, one possibility is that neutrons might be disappearing into this dark matter, this mirror neutron. Of course, you can think of lots of possibilities. And there are other, you could imagine doing this experiment in a similar way, where instead of storing them in a bottle, you're pouring them, and you're using gravity, and gravity is what's letting them pass through the wall. With those kinds of neutrons, you actually do worry about quantum tunneling, because the walls have to be sort of, well, some materials are actually thin enough, I guess, that the gravity can pour them through. You just have to think about how to design the experiment. I don't know that any of those questions are actually answering what you're getting at, but I'm
not a
actually...
physicist, I'm just...
Cover your ears. I'm actually thinking about how to do this with ultra-cold neutrons at a different laboratory.
What are the bottles made out of?
Okay, I'm gonna show you guys a movie. So this is Los Alamos National Laboratory, where I originally got my training as a neutron physicist, and This is a source, one of the most powerful, I think today it's considered the most powerful source of ultra-cold neutrons in the world. But we have a little bit of competition across the Atlantic. What you're seeing are ultra-cold neutrons being produced on the, I haven't started the big video yet, so you're not seeing it yet, so don't worry. But what you will see is ultra-cold neutrons being produced on the left end of the screen, and they can bounce on many kinds of materials. They can reflect off of a lot of materials. They're so low energy, they have trouble penetrating walls. And so this tunneling effect becomes important. So what you're going to see is ultra-cold neutrons can just bounce around in these metal, anything shiny to light, it tends to be shiny to neutrons, so neutrons can reflect off of them. So these are just aluminum dairy guides. We bought them from a dairy farm. These are just dairy guides. Breaks. And you can actually fill this bottle, pour them out into this detector, and every time that light flashes, that's an ultra-cold neutron falling into this box, which is filled with helium-3, which captures neutrons with very, very high probability. So every time you see a flash, this is just hooked up to an electrical signal from this detector. You can actually pour the ultra-cold neutrons into bottles. So it's kind of a really neat, it gives you a really neat handle on different ways to do a lot of these experiments, including this kind. I don't know that I actually answered your question. I might have hijacked it.
Oh, well, really.
So you asked many questions. Maybe I will ask you a question.
Okay.
What the dark matter is made of?
I'm a
What you listening, you might think it is made of neutrons. No.
No, probably everything.
Since Leah's first slide was that it is the same particles here and the same particle there, we have our matter made of hydrogen and helium, as you know, and all the rest is the little things. And in the dark matter, also everything is made of hydrogen and helium. So that maybe in a different proportion, and it is why Leah said that the development of the stars is different, and they live different lives, and something cosmologically can be different, but this is the same stuff.
Okay, so what is dark matter?
Mirror hydrogen and mirror helium mostly.
Does it truly exist, or is it a magnification
No,
of gravity that we don't understand?
We see by gravity that
Where is gravity in the Saturn?
we see that gravity interact, that gravity mirror matter exhibit itself as gravitational effect.
Okay, so
For
where's
example,
gravity standing
Leah
up?
did not explain that, but show that this is a gravitational lensing, which is one
I've
of
seen
the observations, major observation in astronomy now.
But that is not. that
And
would be
this
gravity.
indicate that the number of mirror matter is factor of 5, 6 larger than the amount of the ordinary matter in the universe. And we don't know, I mean, we know with Lee what it is, but general wisdom that we don't know what is the nature of the dark matter. It is not discovered. It was tried this, and that, and nothing worked.
Okay, wait a minute. Grant, general opinion, in the 19th century was ether, in the 17th century it was epicycles. Is
Ether.
there not a possibility that dark matter is magnification of gravity?
There is a community that believes in these modified Newtonian gravity models. Sure.
Yeah.
I would say the majority, the greater fraction of scientists seem to prefer that dark matter is a better fit to our observations. We don't have any confirmed evidence, and I don't think we can say that we believe any particle is the bright representation for dark matter, because we haven't seen that confirmation yet. We haven't seen the evidence of what it is. That's why we're exploring these kinds of these kinds of models to try to find something that could fit
Let's go back
these
one.
observations.
Let's go
You
back.
you
Let's
know
go back
how
one
how
step.
it is work, that somebody say that I see that the dark matter will be made this, and that. And other people said, no, it is not likely, I see it in a different way. But none of them can prove it, first thing. And second, none of them can explain everything. So it has always remained a possibility that modification of the gravity would be explanation. They did not prove that, and there is no facts which are proving that. And it is even difficult to imagine how to measure that. We cannot do gravitational experiments of this kind, which will, but we see it as gravitational lensing, huge effect. So that is how, until you will, 100 theories will exist as hypotheses, until you will start to provide experimental evidence. I predict something, I see it. I predict another thing, I see it again. Then we will go this way and we will find what it is. That's what we are trying to do.
Our time is running short, so normally I would call for a last question, but I'm gonna ask the last question.
That is your privilege.
That's my prerogative. Early on, you said, you brought up, in one of your responses, you made mention of antimatter. So, I'm wondering if you could, talk just for a moment on what would be the difference between, a particle of antimatter versus a particle of mirror matter. Is it like the symmetry, there's some of the axes are flipped and some are not, or what would be an example of that?
The probably most striking difference is that we definitely know antimatter exists, whereas this is a hypothesized particle that we're looking for. Antimatter is a symmetry of charge. It's a particle that has the opposite charge of a regular particle. And this is a very important symmetry because we know that, for example, it's related to a very important question of, why am I giving a talk here and not annihilated, because there's, equal amounts that it's very natural to expect in the universe we should have started with equal amounts of matter and antimatter, and it's strange that we all seem to be made of matter in the universe. So this kind of symmetry is another very interesting one for us, actually. And actually a very related and experimentally and theoretically concept is whether neutrons can oscillate into antineutrons. And maybe that could give us a mechanism by which, if that could happen, and if it can happen and if it's preferred that antineutrons like to turn into neutrons instead of the other way around, maybe that's one way we lost all of the antimatter in our universe. We actually never have seen an example of matter turning into antimatter, so it's kind of interesting to look for this. On the other hand, it's a different kind of symmetry. It's a mirror symmetry. Well, that's not even good. We have parity symmetry, which is left-handed to right-handed, and then we have, I'm gonna have to invent something else, mirror matter symmetry, which is transforming a particle into its mirror partner. And that doesn't actually come with necessarily a change from a left-handed state to a right-handed state. It just comes with a different label on top of your head that says, I'm a mirror particle or I'm not. So it's, a neutron transforming into a mirror neutron, it would still, kind of behave many of the same ways.
So
it's actually interesting to think about, well, anyway, go ahead.
At the start of the video, the guy with the beard made a comment that basically to keep everything balanced out, the rationality of the mirror particle is the reflection of the charge and time saves us in the end in terms of the mathematics of this, whatever. So if antimatter is the flip of the charge, does that kind of suggest that the time that the charge is flipped, but not the time aspect of it, or something like that?
So it's kind of unrelated. You have that sort of triangle of the three symmetries that if you flip one, it's the same as flipping the other two, and those are the parity symmetry, which is different from mirror universe time, the arrow of time, and the charge, whether I'm a particle or an antiparticle. And in the mirror universe, I have the same, triangle of mirror symmetry, mirror symmetry. So it's not that's true in both universes, but it doesn't add to those. It doesn't add to that symmetry. So the fact that time and charge conjugation save you has to be true in both universes, but you can't go from like one to the other. I don't know, this is maybe hard to explain.
Yeah, well, I guess the thought that I had is that maybe conceptually antimatter is not all three axes are flipped, but just one or two.
That's right.
Yeah.
And so, a neutron going to an anti-neutron is one part of that triangle of symmetries, and if you want to make sure the laws of physics are the same, then you have to reverse time, and then you have to reverse parity, and then you're back where you started as far as the laws of physics are concerned. And changing to the mirror universe doesn't actually change anything about that process. So you have triangles in both universes.
So you could have a mirror antimatter particle.
Yes. Yeah.
Well, unfortunately, we can't roll back time here, so I'm going to have to bring it to a close. Let's give our speakers a hand. All right, before we go, we had a door prize drawing, so I'm going to ask my lovely assistant if she'll come up and draw something out, draw a name from out of here. We have, before you read the name, go ahead and pull it out. All right, she's pulled out at random a name out of the cup. So before she reads the name, we were trying to figure out, this is the first time we've ever done a door prize. Maybe it's a good idea, maybe it's not. You guys can help me figure this out. We have two possible prizes. One, we've got a nice $5 gift certificate, and it comes in one color, green and white. And the other is, if you would like to get one of the Science Cafe t-shirts, we will order one for you. There's a shop in a printing company in Seymour that makes these for us. We kind of don't want to be the middleman, so if you're interested in buying a shirt, we'll gladly share the information how you can contact the printing company, and we'll be giving them permission to make these shirts. We laid them out, but they said make them for anybody that wants one. So you can contact them directly. But the door prize, if you don't want the $5 gift certificate, then we'll order you one of these t-shirts. And what's the name on the?
Chris Madison.
Chris Madison. All right. So come see me before the end. And would you like the $5 gift certificate or the shirt?
Gift certificate.
Gift certificate, right here. Here's your man. David's going to bring it over to you. All right. Okay, and again, our website is knoxsciencecafe.org. And if you'll go to that website and look at on the top is a list of links. You can click on the event list, and you can see all of our meetings coming up. And I think while David is talking about the Associated Professionals Think Tank, I'll bring that up on the screen where we can see the next couple of meetings.
I have just a couple of quick announcements. I got 4 copies, they're 17 and 18, of Tennessee Conservationist. If any of you are interested in conservation, please take one or more of those. And if you really like that, I've got 2 ways in which you can order it for yourself. The link is right here. Some people wonder where I get some of the facts for the science factoids that I circulate. Mostly they come from Science News. It used to be called Science Newsletter. There are 2 things here. If you want to order it for yourself, I'll leave those. But I have 3 copies left of our brochure from the Associated Professionals Think Tank. Several of our members were here tonight, and I'm the only one left because they had other obligations. but I've got 3 of these left if anyone is interested in finding out more about that. I'll put those here. And finally, the latest issue of Science Factoids, which is put out by Associated Professionals. I tried something different this time. I put a cryptogram and a Sudoku on the back of them for those of you who like to exercise your brain. So if you want one of those, please pick those up right here.
David,
And I'll
is
be
it
here
possible
to
that
answer
all
questions.
your material will be posted on this website?
Pardon?
How about posting all these materials?
I can
on
do that.
this? I think that this will be
It will
effective way to
save trees,
distribute.
won't it?
Yes.
Okay, that's a good idea. Okay, so if you go to knoxsciencecafe.org, you'll come to the homepage for our group here, Science Cafe, and you can see tonight's meeting, Mirror Matter, was on the home page. So if you go up here to the top and click event list, you can see all the past events by year. The current year comes up. We're here in October. They get newer as we go up. So our next meeting will be on November the 7th. The topic is going to be mountain medicine, the science of search and rescue. And our presenter is Bill Campbell. He's an MD. And he left his family practice to go get specialized training to do delivery of medicine and health services, rescue services to people who are on high peaks or whatever. Basically, if you're hiking Mount LeConte and you break a leg, he's going to come flying up there on a helicopter to come get you, all right? So that brings up the possibility that at 4 o'clock on November 7th, he might get a call that he has to go rescue somebody. So it's possible that he might not be here that evening. His wife's going to substitute in that case. But that's the topic we hope to have next month, mountain medicine.
And they're both here tonight.
Oh, I'm very glad. I'm very glad to know it. I didn't see it. All right. Let's see. And then in December, we have a returning speaker. Some of you might know Stephen Lynn Bales, retired naturalist from Imes Nature Center. He is currently caring for a type of falcon called a kestrel, and like many falcon species, like American bald eagle, that are bouncing back from near extinction, the kestrel is not making a comeback, and so he's going to come and talk about why they might not be making a comeback. But he'll have his falcon with him here. David, have we checked to make sure that that's all right with the library?
I think they've had animals here before.
Okay.
So I'll double check.
Okay, thank you, David.
I don't think it'll be a problem.
So if you click on 2020, that'll be on December the 12th. If you click on 2020, you can see the events for next year. We have 2 meetings, January 16 and February the 6th, where we have a reservation here, but we don't have a speaker yet. Susan Garwecki, is that a possibility, one of those 2 dates? You might be able to come and talk about llamas?
Maybe.
Maybe. All right, talk to me a little bit later. It's January 16th and February the 6th. And who else was it I talked with tonight about a possible...
That's the library, not llamas, too.
Okay. So, anyways, and then our next scheduled meeting in 2020, we have a confirmed speaker on March the 5th, Tammy Jubanali, and she has just written a book called Iceland, Tectonics, Volcanoes, and Glacial Features. And she's going to come and talk about the research she did on the geology of Iceland. So that'll be March the 5th next year. We try to plan these out about 6 months in advance if we can, and make sure that we can get our room and our speaker and our topic and a video all lined up. If you know anybody that'd be interested to come, they're doing research, they're experts in their field, and they'd like to present, we welcome all topics. I think recently we've had quite a lot of biology topics this year, but we do chemistry, we've had nuclear engineering, we've had some physics. It's been a while, and I'm so grateful you guys came tonight. Thank you so much. We like all different kind of topics around here, so if you know anyone who'd be interested, have them contact me, and at the bottom of the webpage is a good address, contact@spiritedtruth.net. So we thank everybody for coming, and hope everybody has a nice evening.